Good afternoon, St. Mary's freshman physical science class. Today we're going to be talking about balancing chemical equations, and to give you a little bit of a real-world example here, we're going to be talking about global warming. We'll be talking about, of course, the increase in the population. As you can see here in 1950, we were under 3,000 million, which would be about 3 billion people. By 1993, we were just under 6 billion people, and by now, we are far over 6 billion people. What this has caused, of course, is a massive consumerism, which has caused many people to have cars, and those cars also kick out a lot of carbon dioxide. So these traffic jams is just a extreme example of a mass production of carbon dioxide based on a chemical reaction in the equation. So this is a decent comic over here from Dover. I'll give you a second to read it. So as you can see, we have a employee here that's a little not getting his job done. His boss doesn't know why, and he tells him because it's because of global warming, and he's giving his boss a hard time for being a polluter. However, he is correct that the increase in carbon dioxide has gone up. Now, back here in the 1700s, this is when the Industrial Revolution occurred, so we have a little bit of an uptick going on there. 1850 was the second Industrial Revolution. Of course, now in the 2000s, we have a time frame where we have massive amount of cars and work materials all running on fossil fuels. Right? So here is the primary world consumption of their energy resources here. These are petroleum, which is the gasoline that you put in your car, natural gas, which is the stuff right on top of oil in their oil pits. Coal, okay, this is a fossilized plant fuel. And here's hydroelectric, nuclear power, and geothermal. This is the type of stuff people are putting in their houses to heat it and whatnot. Wind and electric power. These are the things that are considered quote-unquote clean energy. Nuclear electric power obviously has incredible waste issues, but for the most part, a little bit does not produce carbon dioxide. These three things actually are carbon-based materials, which in the presence of oxygen will actually break down and form carbon dioxide. So here again is another graph that shows us how petroleum, coal, and natural gas are used. Again, is the total amount of carbon fuels that are used is the black line. Petroleum came along, especially when people started driving their cars more. This was trains and mass transit was using coal power, especially for ships and whatnot. So eventually it has turned into more of a petroleum type of oil that we've used. Again, natural gas is coming along here as far as million metric tons. All right, so here's the basic equation that we're kind of going to be working from as far as this part of the talk is concerned. Anything that talks about carbon-based molecule is talking about something that has been living before. So you're talking about fossil fuels, you're talking about coal, petroleum, and natural gas, all things that are produced by organic living things. So in the presence of O2, they produce carbon dioxide, which is probably the thing that we're most concerned about, water, and in the main portion, of the equation. The reason why we want to do these things is because we want to produce energy. So now, the reason why we're so concerned about how much carbon dioxide we put, and we're going to do this chemical reaction actually in a couple of days, but for the most part, what ends up happening is it holds on to energy a little bit more. So you can see as we've been consumed more and more carbon dioxide type of materials. You can see 1915 to 2000, the average temperature 1950 to 2000 has also increased. So that's kind of a big issue going forward. Now, why is that such a big issue? Well, in that chemical reaction, we hold on to more carbon dioxide, we hold on to more temperature, which in theory, and this is more of a hypothetical type of graph, but in the worst case scenario, you could see the energy levels, or not the energy levels, the sea level rise almost 11 meters from 2000 into 2500. So that's a huge increase. If you think about 10 meters into the air is what that water would rise. So that would greatly affect a great many cities in the United States and around the world, and at least And the least case scenario would be just above 3 meters, which would still be a huge issue. But this might turn into this type of situation where we have Santa Claus and the polar bear just kind of hanging out together. Now, what we're talking about here is the conservation of mass. And so what we're trying to get you to understand from a global perspective is, even when you're driving your little mopeds around or you're driving your cars around and whatnot, that matter has to go somewhere. And this matter in particular is causing an increase in temperature, which, if left unchecked, would become out of control and would extinguish any life left on Earth. So the law of conservation of mass is basically saying if you start with something, CH4 and O2, that matter has to go somewhere. Well, in a chemical reaction, this particular chemical reaction turns into water and carbon dioxide, and we're trying to get energy out of it. It's an exothermic reaction. Okay, so the equation shows that the reactants that you start with, you also will end with. So what we need to do is understand, number one, how to get that conservation of mass. And what that's called is balancing the equation. So we're trying to get the same amount of matter on the reactant side on the left and the product side on the right. So balancing equations requires you to make a number of each atom on both sides, the reactant and the products, equal. Okay, we'll talk about that. We have a couple of simulations that will help us with this. But place the coefficient in front of the formula to change the amount of atoms. So coefficient is referring to a number, a whole number that we're going to be using now. It's not a fraction, it's not a decimal, it's a whole number. Right, so when we look at a chemical formula here, H2O, it represents 2 atoms of hydrogen and 1 of oxygen. So H2O is what that would represent. So in this case, we would have, sorry, I need a pen, O and 2 H's. Okay, so that is H2O. Now, if I want to put a coefficient, this is what that's referring to. This is a coefficient. Okay, coefficient out in front of that. That 2 would mean that we have 2 oxygens, 2 waters. That increases the total number of atoms of oxygen to 2, 1, 2, and the total number of hydrogen atoms to 4, 1, 2, 3, 4. Okay, so that's kind of what that's referring to as far as how a coefficient works and why you would do that. So what this is showing us is that we can increase the number of atoms on one side of the reactant one side of a reaction, excuse me, simply by changing the coefficient out in front. What the coefficient is showing you the amount. Okay, this is how much water reacts. Okay, and what ends up being what's called the mole of the reaction is what that's called. So here's a question for you guys to answer. In this particular equation, go ahead and pause. This is what this is going to look like. All right, so we have calcium is in red, nitrogen is the green, and O3 is in blue. So if I have a coefficient of 3, how many of each atoms would I have of calcium, nitrogen, and oxygen? So this is a good reference point for you. Not everything, but again, if I put a coefficient of 3 out in front of it, how many molecules does it give me? Okay, go ahead and push pause, and you can go ahead and figure that out. So now after you've hit pause and you push play again now, you should be able to tell me that we have 3 calciums. We should be able to tell me that for every calcium you have 2 nitrogens, just like this. So if I have 3 of them, that means I have 6. And for every calcium I have 6 oxygens. So if I have 3 times 6, that gives me 18. Okay, you can go ahead and push pause and look at my logic if you'd like to. But that's the basic idea of how a coefficient works with a little bit more complicated problem. The idea is that when you're balancing equations, you must count all the atoms to make sure that you can balance them on one side and on the other. So now, when we're balancing equations, we need to go through simple 4 steps. Some of you will go through these steps rather quickly. Others of you will need to go step by step just like this. So first of all, identify the reactants and the products. Count your atoms, insert coefficients. This is probably where the majority of the work goes into, and verifying your results. So now, the first step, we need to go ahead and figure out what are our reactants and our products. Now, for the most part, you guys understand on the left side, this is reactants. On the right side, these are the products. Okay? So anything that's over here is a reactant. Anything over here is a product. So I went ahead and filled this out for you. The reactants are sodium and water. And my products are NaOH, which is sodium hydroxide, and hydrogen atoms. Okay? So I've gone ahead and figured out my reactants and products. Now my second step, I need to count my atoms. So I've went ahead and filled this out for you, and we're going to talk about the third column here in a second. Sodium, if there is no coefficient behind it, or not coefficient, no subscripted number that's telling me I only have one, I have 2 hydrogen atoms, that's 2 right behind there, so I'd mark a 2 down here. And of course my oxygen here does not have a coefficient behind it, meaning that there's only 1. Same thing with my products, 1 sodium, 3 hydrogens because I have 1 hydrogen here, 2 hydrogens there, that's 3, and of course 1 oxygen atom. Okay. My third column is telling me if I need to balance the equation or not. My sodium atoms, I have 1 to 1, so that's balanced. My oxygen atoms are 1 to 1, that's balanced. And my hydrogen atoms, I have 2 to 3, so that's not balanced. So obviously, I need to balance this equation. So to do that, we need to do a little bit of work. A couple of, or one thing to really keep track of is this right here. Make sure that if you have an odd number of something, turn it to even. That will kind of help you. And also, you need to reduce. You need to have the lowest terms as far as the coefficients are concerned. Okay, so when looking at this, again, we had 3, 2, 1, 1, 1, and 1. Okay, these are the number of atoms on both sides of the reaction. Okay, so again, working with this whole odd to even premise, if I have 3 hydrogens over here, I need to take that to an even number, and the only way to do that is to create a 6. Okay, so I need to have 6 hydrogen atoms over here. I need to have, and I'm sorry, I'm jumping ahead on you here a little bit. The idea is we want to create a even number out of this. Okay, so when I look at my materials here, I can either change this coefficient by putting it, let's just say we put a 2 out in front of it because that would change the amount. This would give me 4 hydrogens there, 1 hydrogen here. I still have 5. Well, that's not an even number, that's an odd number. Okay, so I need an even number. Well, what happens if I would put, let's just say, a 2 out in front here, which changes the amounts of all these things. This gives me 2 hydrogens here, 2 H's. Okay, and I have 2 H's here. Okay, gives me a total of 4. All right, well, now that's an even number. Okay, so let's go ahead and do that. So we'll leave a 2 there. And we'll take this and we'll change it to a 4. So that's how it's changed so far. So then that means I need to take this and change it to a 4 as well. In order to make a 4 over here, I'd use the coefficient of 2. 2 times 2 equals 4. Okay. So now this has changed a few other things. So we have to keep track of all these materials and these atoms, excuse me, as we go along here. If I put a 2 out in front of sodium hydroxide here, 2 times 1, since there's no coefficient or no subscript there, that means I have 2. So then that means this gets changed to a 2 just by adding this number here. So that means I need to have 2 over here. In order to do that, I would need to put a 2 for a coefficient out there. So that means I have 2 sodium, 2 sodium. I have 4 hydrogen, and I have 4 hydrogen, including both of these compounds. So now let's look at the oxygen here. I have 2 oxygen here, and now I have 2 oxygen here based on those subscripts. So based on what I've seen here so far, my best answer is 2, 2, 2, 1. There's no way to reduce that any further because we have a 1 right here, so 2, 2, 2, 1. Now, as far as writing this out, you could leave this blank, or you could put a 1 there if you'd like to. No big deal, one way or the other. So my answer turns out to be, the correct answer, turns out to be 2, 2, 2, and 1. Okay, so that's the best answer. So now we need to go ahead and verify our results. So again, there's my answer, 2, 2, 2, 1. So now, we're going to verify our results. To do this, we're going to go ahead and use the conservation of mass. You have to make sure that both sides have equal amounts. So there's 2 ways to do this. You can either count every single atom like we did over here. Okay, we counted every single atom. Or we can go ahead and do the opposite and a very similar way and talk about the conservation of mass. So again, they balanced the equation here, 2, 2, 2, 1. We can look at the total mass of the reactant. So 1 mass unit of sodium is 22.98. Since I had 2 of them, I have to take it times 2. And I had 2 waters, so water's molar mass is 18.02. Take that times 2 again, my coefficient is 2. Total amount of mass between these two things after the math is done is 82 grams. Okay, I can do that with my products as well. 2 sodium hydroxides is 39.98 times 2, and 2.02 for the element of hydrogen times 1 gives me a total mass of 81.98. Now, 0.02 is pretty decent as far as the math is concerned based on all these numbers, how they're rounded. So my reactants, 82 grams, do equal my products, 81.98 grams. So did I verify my results? Yes, they are done. Now, you don't have to necessarily go through all those. If you get a pretty decent just balancing the atoms, if you're good at seeing that, you can do that. If you need to go further than that, this is just another way of tying the conservation of math back into what we're talking about. Okay, so what's the point of all this? Well, number one, if you're going to balance the equations, you can't change the subscript. As you can see, I'm moving the circle around over here. You can't change that little red 2. So this is the right way if I was going to try to balance out hydrogen and oxygen reacting to form water. I would have to change the subscript 2 out in front of it. The coefficient 2 out in front of it. I cannot, in order to balance this equation, change the subscript behind it. H2O is water, H2O2 is hydrogen peroxide. Completely different chemical properties, completely different substances altogether. So make sure that you do this and not this. So right way, wrong way. All right, so we'll move on to classifying chemical reactions later. So biggest thing here is understanding that when you're burning your fossil fuels, that eventually everything, all that matter is conserved somewhere, and we might end up like this. So thank you very much.